But you know, we can split it. We can do Paraview and consulting. No, that's just left for people to look for.
No, it makes us look rational.
Good morning. The question has become, well, did you send Paraview slides to Jason?
Yeah.
And when you do your Paraview section, are you going to split screen up there?
That's what I wanted to do, yeah. Have one slide and one with the demo.
Well, hello everyone. For those of us that are listening online, we're going to start in about 5 more minutes, maybe 10. So just to give everybody a heads up. And my name is Jason Allison, and Greg Abrams will be presenting for us. Thank you.
Abrams, singular, no S. Right up there, no S.
Sorry about that. Greg Abram, I apologize.
I'm sorry, I'm very sensitive. No. Tell me something. Yes.
You have to listen to
Yeah, like so 4.3 is not the building now?
Yeah, just like the widgets weren't filling in properly for some things like the calculator. You know, I added a calculator and it wasn't displaying the meat of the widget, it was just displaying like the top part. So there's a couple things like that where they didn't, I mean, it worked fine sometimes they weren't working correctly.
Good.
So,
Good thing I haven't put that as
yeah,
going up 4.3.
yeah.
So what's the standard one we're using is 4.3. The 4.3 has come out and it's reporting in Avalon 3.8.
Everybody who's with you.
Does that have okay.
It's going to pick up all the mic on this graph.
So you don't want the room mic?
We'll go down that.
Sure.
Oh.
Hey, how are you?
Okay. All right.
I gave them the solution. First of all, I gave them the work on the actual solution. And the response was, okay, thank you. We'll decide what we want to do. I thought that was pretty bizarre.
You're going to take everything else instead of half
This been the multiple slides.
Okay, let's get this show on the road here. I am Greg Abram. I work here at the Texas Advanced Computing Center. Welcome to TACC. We are a supercomputing center that's got some big computers and do a lot of science here. And so we have a visualization group, and I am a member of that visualization group. So why do we do visualization? This is the platitude section of the day. Ancient Chinese person allegedly said a picture's worth 1,000 words. And I actually ran down that phrase, and it seems to come from an advertising journal. But they did have a point. I mean, ultimately, our visual cortex is a great tool that we have to understand stuff. And what we do in the visualization world is we leverage the visual cortex in order to help us understand information in it's very abstract in its basics, but do it in a visual way so that it makes sense. Here is the sort of classic example of why visualization is useful. This is 4 little tiny data sets, each with only 10 points in it. And if you look at it statistically, these 4 data, well, first of all, these 4 data sets differ, right? But if you look at them statistically, they're identical. The mean and variance correlation and regression equation are identical for all 4 of these data sets. So statistically, it's very difficult to look at these numbers and understand anything about them, except that they're basically random points in space. But if we plot those random points in space, more information comes out from them. So remember, statistically it's the same, but clearly there are patterns in this data. There's relationships between these data points that come out instantly when you look at them plotted that you would never think of if you looked at them strictly as a bunch of numbers on a page. So this, I think, shows very, very clearly that looking at data, that taking data and transforming it into visual representations is an incredibly useful tool. I think we all know this, and I'm basically beating a dead horse here. But it's clear that showing data using visuals is an effective way of understanding what that data is. Here's another interesting data set. This is a data set describing Napoleon's invasion of Russia. And if you look close here, you will see that we have the longitude and the latitude of his army over a certain number of days. Actually, here's actually over these days. You have the size of the army. The army actually splits into 2 different groups and goes in different directions at different times and reforms and so forth. And you can see some rough information here just by looking at the numbers. You can see that the number of survivors, it's not a pretty picture here, right? But possibly the most famous visualization of all time is this one. This is that same data being represented by a guy named Menard, being represented graphically. And so that data is all being combined here into a single picture. And the single picture is showing you the path that the army takes, the size of the army at each point in time, how the army is splitting apart into different sort of sub-armies. And basically you see here graphically the whole story of the invasion. And this is the same data that we were looking at a moment ago. Starts out with a huge army here on the Russian border, gets as far as Moscow, turns around, and it isn't a pretty sight, right? Tiny little fragment of the army remains. And if you actually look, this graph down here is showing you the temperature the maximum temperature of the day over that period of time. So you can see that as the Army is coming back, the temperature is actually the return trip. It's getting colder and colder, and boy, I'm glad I wasn't along on that trip. Here's another data set. It shows casualties of the Crimean War. And here I mean the one back in the 19th century and not the one in the 21st century. Again, a bunch of information. Here is a very interesting graph. This was done by Florence Nightingale. How many people here have ever heard of Florence Nightingale? What is she famous for? She's a nurse. She was also a statistician and developed techniques for showing that information. And here, the point she wanted to make was the majority of deaths that happened during this period of time was not due to combat. It was not due to people fighting. It was due to disease. And she wanted to come out to take the numbers that she had acquired and present them to Parliament to make this case that the real problem wasn't the battle, it was basic health, basic medicine. And so what you see here then is time going around. Actually, for all intents and purposes, this is a bar chart where each one of these bars is showing you the number of people that are casualties of battle and the number of people that are casualties of disease. And you can see it makes the point quite clearly. But I think it's really interesting that that was, in fact, a famous nurse who did this. A lot of the original transformations of data into graphs were done by this guy, Joseph Priestley. A lot of these things that we look at in the newspaper every day seem so obvious. Representations of data into graphs and into bar charts and things like that. But somebody had to invent that the first time. And this guy, Priestley, invented a lot of them. This is a representation of the overlapping time of famous people from ancient Greece, I think, over time, and shows you how they lived. Greece and Rome, I guess I see over here, Brutus and Caesar. Playfair invented the bar chart and the pie chart. So we have lots and lots of techniques for transferring data to images. And a lot of those techniques, they differ because there's a vast difference in the kinds of data that we want to convey to people. Basically, we break, in my business, we break the data that we deal with into two fundamental classes. One of those classes we call InfoViz. It is data that basically represents a set of facts. And here you can think of that data as, its standard representation is Excel spreadsheets, right? Where each row in an Excel spreadsheet is telling you a fact. There is a person named Joe who is 46 years old and has cancer and got this medicine, right? And so there's going to be a database that has all the patients in it and the fact that these patients exist and have these characteristics. The other kind of data that we deal with is what we call sci-viz data. And this is where this is a little sensitive because a lot of scientists generate InfoViz data and they want to think of their data as scientific data too, yeah. But we call this other kind of data sci-viz data because it represents physical properties defined over physical spaces. So for example, we could have a sci-viz data set that describes the temperature in this room. And we could do that essentially by creating a grid that fills this room, a three-dimensional grid, so that at every XYZ point in that grid, we list the temperature. And from that, we can interpolate the temperature anywhere in the room, right? So it's a continuous field. It fills this whole volume of space. It's not a set of discrete facts, but it is a representation of a continuous space and the properties that are defined on that continuous space. So aside from those two basic classes, there's any number of other different kinds of data that we want to be able to visualize. A lot of people are interested in molecular graphics, molecular dynamics, things like that. They basically have information that tells how atoms are positioned in space, how they're moving, how they're connected to one another, and so forth. Genomic data has to do with the sequence of nucleotides in a linear string, and how that string can be wrapped up using molecular dynamics, and all these things sort of interrelate. But my point in this part is there are two large classes of data and then vast numbers of other kinds of data that also need their own visualization techniques. And in this class, we are going to be dealing primarily with the first two of these. Information visualization, because it's such an important area these days within the big data revolutions. And we do deal with that here a lot at TACC. But quite honestly, our focus here at TACC is high-end scientific simulation. That's why we have these immense computers that you probably noticed as you walked into the down the hall here. And so sci-viz data is my expertise, and it is really mostly what we do here at TACC, and why you would come and use TACC resources and TACC personnel to do visualization stuff. So there will be a much larger focus on sci-viz data, but I will speak a little bit about information visualization just so you have the sort of parameters of it. So like I said earlier, information visualization is essentially the visualization of large numbers of facts. And those facts can take on any number of different categories. Again, put your head in an Excel spreadsheet, you know what I mean. The different columns of the spreadsheet are different attributes of each one of these facts, and the horizontal, the rows, are the facts themselves, right? So for example, there is a fact which is a person's, like I said earlier, a patient's state in a hospital. And that might be his name, his age, and his disease, and what his treatment is. Each one of those columns can take on different qualities. You know, actually, I'm not really sure where this is going here. Let me just look at a couple of, yeah, okay. This is basically beating you over the head with the notion, with the distinction between InfoViz and DataViz and SciViz. The overall goal in information viz is to represent not only this set of facts, which you can see by looking at a Excel spreadsheet, but it's to show relationships between those facts. For example, one of the sort of classic studies in information visualization comes from a list of movies, their directors and actors, and produces a visualization that looks like this. This is the famous Kevin Bacon data set. This basically is a representation of how different actors and different movies are related to Kevin Bacon. So the arcs here show what Kevin Bacon did in each one of these movies. And out here we have other actors. And basically what this is doing is it's showing you how Kevin Bacon is related to all these other actors by having participated in the same movies with him. Kevin Bacon is an actor. He acted in several truly wonderful movies like Footloose, and my personal favorite was Tremors. If you get a chance, check out Tremors. Okay, so here we have a representation of this data set that has been created by interpreting that data set. Okay, so the data set itself it had all this information, all this representation, all of these relationships in them, but that was not the direct focus of the data set. The data set was simply a list of movies, actors, and directors. And movies, actors, and directors. And this is an extraction from that. This is a way of taking that data, deciding what you want to know from that data, and generating an image that conveys what you want to know from the data. So this is a pretty classic form of visualization. Like I said earlier, scientific visualization, again with apologies, is data that represents physical properties over physical spaces. And the sci-viz experience that everybody in the world has, everybody in the developing world has, is weather maps, right? Everybody turns on the 5 o'clock news, 6 o'clock news, and they see representations of a simulation that the USGS, or the God knows who, performed overnight and has been interpreted as graphics to show them what's going to happen in the weather tomorrow, right? And so the maps that you see, the representations you see in the evening news are are visualizations of scientific data. So for example, the domain might be the physical space over the Southeast United States. The physical properties might be the temperature, pressure, and the wind at every point in that space. So it is essentially a function from latitude, longitude, altitude, and time to these properties. And now given that we have that function, we can visualize that function. So this is NCSA, National Center for Supercomputing Applications, a visualization of, it looks to me like a hurricane, or at least a large rotating storm off the coast of Florida. So this is a visualization of essentially that function. And we'll talk later about how you represent that function, but essentially this is a way of taking data, which is a function of latitude, that way, longitude that way, altitude that is that way, and producing properties and giving you a picture like this. But of course, this is a much more likely picture that we're all familiar with. You know, latitude, longitude, time as the thing evolves during the day. And this is a way of representing the temperature, I guess, at ground level over that space. So this is scientific visualization. This is classic scientific visualization. And this is sort of, and everything else that we're going to be doing in the sci-vis world is basically analogous to this. There's a third class here that deserves to be mentioned because this is sort of what a lot of people are familiar with, and that is scientific illustration. Scientific illustration is different than visualization because it's not intended to convey data, it's intended to convey ideas, okay? So for example, some people here did a wonderful visualization of blood flow through arteries carrying packets of medicine and being deposited on the surface of the arteries in order to put the medicine where it needs to be. And they illustrated this with a really nice visualization, but it wasn't driven by data, right? Each one of those little packets was not scientifically described and plotted through space. It was an illustration of the idea. So yeah, I think I wanted to show here though one of these scientific illustrations that really got me interested in graphics, computer graphics and visualization way back when we were first shooting satellites up into space. There's not a soul here other than me who's old enough to remember this. But back in the 70s and 80s, we were putting up satellites, and there were these videos that would come on the news to hype this stuff, and they would show, well, let's let it, oops, wrong. Let's see. How do I start this thing? There we are. And they would show, it was always captioned, NASA JPL simulation. And this is all an illustration of what's happening with this satellite, which you'll see in just a moment. So here we have Saturn, and soon will come in the satellite. And this is totally not data-driven, right? This is Jim Blynn's model of what Saturn looks like. You notice he wrote a SIGGRAPH paper on these little features here. Here comes our satellite, and this is meant to illustrate that the satellite is floating around or traveling around Saturn, and to give people an impression of what's really going on. But again, it's not data-driven. It's not driven by the actual path of the satellite. The satellite is a rough approximation of what the satellite really looks like. And this guy down here, Jim Blinn, is one of the gods of computer graphics. He developed a lot of the techniques that we are familiar with in pretty picture graphics. And I saw these things as a kid. I just loved them. I couldn't believe you could do this sort of stuff with a computer. And that's sort of where I got into this mess many years ago. You notice the shadows here. He developed that technique. He developed the modeling of the rings here and got high-powered scientific papers out of all this stuff. And old Jim Blinn, he's pretty amazing. Okay. So let's think for a moment about what the process of visualization actually is. At the beginning of the process here, we have some data source, and that data source can be a lot of different things. It can be I mean, the one we deal with here most is simulations, where you've got a big program that's running on Stampede back there and cranking out numbers that we want to visualize. But the data source can be other things too. It can be measurements, it can be instruments that are distributed and acquiring information that we want to understand. Data can come from lots and lots of different places, and bringing that in is an art in and of itself. Once we have a data source, the next thing we have to do is come up with some representation of it so that computers can store it, so that computers can understand what it is the data contains in sort of a very sort of fundamental level. Once we have that data, or once we have the data represented inside the computer, we can start applying algorithms to it that essentially derive visual aspects from this raw data. So there will be techniques like extracting contour lines and choosing where you want to clip data and all sorts of things like that. Once that happens, the result of that typically is renderable geometry, triangles. And we have to pass that into a rendering phase where those triangles are combined with a position that you want to see them from and a screen that you want to put the pixels up on, and you actually generate pixels and generate pictures. And then those pictures have to be actually displayed. So this is the standard pipeline where data starts out, passes through these processes, and shows up on a display device. But it's a feedback path as well. Once we're looking at a display device, we might want to change the view. We might be looking at Saturn there and seeing the rings, edge on. It's not quite as exciting as if you rotated it around, you saw them, obliquely. And so you might want to be able to change the view once you've seen where you started. You might want to change the techniques that you're using to visualize it, or change the parameters of those techniques. So instead of looking at a contour line at altitude 2,000, you might want a contour line. You might decide that an altitude of 1,000 is more interesting. So you might have a feedback that goes from what you're seeing back to the algorithms you're using to generate what you're seeing. You can go all the way back to the data representation and decide that the representation that I use for this data is inadequate. It's not finely defined enough so that I miss tiny details of it. I might have to go back to the way that the data is being represented in order to make sure that my representation captures the information that I want to actually see in my raw data. And ultimately, you can go back and you control the data source itself. We use a technique in the supercomputing world called computational steering, where we can look at what's happening inside a simulation as it's running and decide that we want to tweak parameters of that simulation. And we can change those as the simulation is running so as to steer it in the direction that we want it to go. Okay? So now, or you can, for example, you can redirect instruments to acquire information that's more interesting to you. You can reposition a satellite so that it focuses on the area of your particular interest. So the point of this is that the visualization process is not a one-way path from data to a picture, but it's a feedback loop where you learn from what you're looking at, you learn more about what you're seeing, and you can adjust how you're pulling that data out to learn more about what you're really trying to understand. And so I think this is sort of the critical point for doing really high quality scientific visualization, is to support this kind of loop as flexibly as possible. Now, given that, I just wanted to show you some of the visualizations that we've done here. Anne, could you turn off the main overhead lights? I just want to sort of give you a broad range of the sorts of visualization that we do. There's an organization, a research arm of the university that's interested in transportation research. Anybody who gets stuck on MOPAC ought to wonder why these guys get paid. But nonetheless, they have simulations that model how traffic happens over networks. And so this is a tool that we built here at TACC to take the result of their simulation data, which essentially is just rafts of numbers that correlate, that represent numbers of cars on what roads at what times, and provides an interactive means for exploring that data. This is a project that was being done with, I think, NARA, National Academy of Research Archivists, something like that. Anyway, they're really interested in figuring out how you take very large amounts of documents and present those documents in a way that allows people to quickly search and find the documents they really need. Okay, card catalogs are the most primitive possible form. You take this information that is multivariate in ever so many ways, and you generate essentially a sequence. You order them along the rows of your card catalog. It's pretty crude. This is a visualization of a very large set of documents that they have created so that you can interactively explore in multidimensional space. So people here at the university are very interested in how disease spreads. And they're interested in it not only from a purely scientific point of view, but they want to be able to put decision makers in front of data simulations so that they can answer questions about where to, for example, position, antidotes, medicine for the flu. Okay, so they want to know if the flu breaks out in Texas and we put flu medicine in, and we pre-position flu medicine, can we affect how much the flu affects Texas? And so they have a simulation that models how the flu spreads, and this is a tool that we've built so that people can game out the idea of pre-positioning remedies and in order to alleviate the problems. These guys are interested in the magnetosphere of stars, and this is a representation of the magnetosphere of a star. I don't know how effective this is at conveying the underlying data, but it makes for a heck of a picture, so I'm putting it up here. This is information looking at turbulent flow. So you're interested in how flow through a volume changes through time. In steady state flow, think of it as low speed fluid moving through a pipe. It's pretty constant. But when fluid gets fast, weird stuff happens inside the fluid flow. And people are really interested in that. It's a pretty important area of research. The problem with turbulent flow is that it's very what we call high frequency. So you have to do the science at very high resolutions. And here, there are only 17 time steps of this data, but they end up with 34 terabytes of data for 17 time steps. So you take this data set, you take 17 pictures of it through time. 17, you dump out the data 17 times through the simulation run, and it is 34 terabytes of data. So this is a really big data set, and that's sort of our bread and butter here, is how you deal with these very, very large data sets. This is one I really like, largely because I did it. These guys at ISIS on campus are interested in the physical structure of the Earth. And so they have created a model that describes the physical structure of the planet. And what they want to do is they want to decide whether their model is correct. And the way they do that is they model earthquakes. Once an earthquake actually happens, you simulate the same earthquake. And if your simulation matches what really happened, then you know that your simulation actually represents reality, right? So this is a model of the Japan earthquake. And they essentially created a shock here, and they're able to propagate the waves of that shock through the Earth. And if I had this in actually running as an animation, this would be much more clear. But basically, you see the shock wave of this earthquake as it moves throughout the entire planet. And yes, it goes all the way to the other side of the planet and back. And they have sensors that are positioned out here on the surface of the Earth everywhere. And so the question would be, at this point here in Iceland, what shock was actually measured by their seismographs? Iceland has a lot of seismographs. They have lots of stuff happening down there. How does the simulated shock wave match the measured shock wave? And by comparing those, they can figure out how good their model is. I described this one a little bit earlier. These people are doing what I consider to be illustration of the deposition of medicine through an artery. And so they've modeled the artery, they've created some visualizations, some illustrations of this all happening in real time, models of what the arteries look like in the chest. And this is scientific illustration, illustrating the ideas behind their research, as opposed to, actually, I guess right down here, you're actually seeing what we call sci-viz, because they have simulated what's happening in these arteries, and we're looking at what's actually happening inside them. This is more of a flu outbreak, except this is, instead of just in Texas, this is across the whole country, and they're interested in modeling how flu travels over, once it's started somewhere, how it expands over the whole country. Can anybody guess what the main paths that it takes are? It is the paths that connect the hubs of airlines. That's where flu spreads from hub to hub. Okay, that's our gallery for the moment. And this is what we're going to do today. I'm going to give more information on scientific, a little bit deeper dive into sci-viz, and then we're going to have a break. Yeah. Then there's going to be, I'm going to give a talk about information viz. That one's probably going to be kind of boring and simplistic because I really don't know what I'm talking about. Then Ann Bowen is going to give a demonstration of doing scientific visualization with Paraview. Paraview and Visit are two of the general purpose high-end visualization packages that a lot of our work here at TACC uses. So understanding how those two guys do the job, I think will be very helpful for you guys to not only use those guys, but to sort of understand how these tools are used so that other perhaps more domain-specific tools that might be pertinent to your particular domains can be used. So Anne will be giving the Paraview talk. Simon will be giving the Visit talk. Later on in the afternoon, I'm going to be giving talks about remote visualization and parallel visualization. We're going to probably swap those two around. We provide tools here at TACC for doing visualization, but our users are not necessarily here at TACC. So we need to be able to provide them with visualization tools wherever they actually are and not require them to come here to Austin, blessing though that may be. We want them to be able to use our visualization tools remotely. So we've developed technology to do that, which we want you to understand. Also, a big part of our bread and butter is parallel visualization. We deal with some of the largest data sets in the world here. Department of Energy National Labs probably has more than we do, but we deal with huge data sets. And doing visualization of these huge data sets takes a lot of horsepower, more than your office computer is going to be able to deal with. So you do need to look at how you can do those sorts of visualizations, sharing the work over a really big, really distributed machine, rather than doing it all in one place. So I'm going to give a talk on that. Finally, later on in the afternoon, we're going to do what I call a workshop. We're going to entertain any questions you guys have about what you actually need. And I'll have Anne here and some other colleagues, and we can help you on a one-on-one basis or any open discussion that you'd like to have, and we'll just make that sort of free form. So that's our day. We want this to be as interactive as possible, so that we believe in interactivity here. We want this to be as interactive as possible, so if you have any questions about anything that's being said here, please speak up, and we will try to keep this stuff as close as possible to what you guys actually need. Okay, so let me go right into the scientific visualization stuff section. Okay. Okay, now we're going to look at an introduction to scientific data visualization. I, in fact, am still Greg Abram. Now, belaboring the point. I've said all this just a few minutes ago. Pictures are worth 1,000 words, absolutely. Nobody doubts that. Here is a scientific data set. This is a representation of some attribute. Let's see, we can probably tell what attribute here. Group ID, format, I don't know. It's some attribute over a grid that is basically 50 by 50 by 50, and here are the numbers. And to belabor the point, God knows what that data actually means. But we can use tools, here visit, which I mentioned a few moments ago, to interpret that data. And now this is a visualization of that same exact data set, and you can see something about what that data actually means. Okay, so that in a nutshell is what we really do here. We take data that is rafts and rafts of numbers, think Manhattan telephone books, and generate pictures that convey their data. This data is usually a function of some domain, the volume of space in this room, the air over Ohio, and at every point in that space, there's some set of attributes. I keep putting my laser pointer down here, and that doesn't really work, does it? Those attributes are things like temperature, wind direction, and stuff like that. And this is in fact what we do inside of visualization, is visualize that function. So let's look for a moment at what we might really be talking about. Here is a 2D height field. It is a function from latitude and longitude, so latitude and longitude, and it gives elevation. So you could think of it as just being a whole raft of numbers, the elevation at every point in this latitude, longitude space. But now we're just representing that elevation as color. We're using a color map to false color this image and show you now that here's a scale that tells you that the darkest blue parts of this thing are about 1,600 feet high, and the highest points are more like 2,100 feet high. And so this gives us a way of looking at how that data is spread over space. Here's another way of looking at that data, where instead of looking at it as a color-mapped surface, we're actually elevating the surface, right? So now the surface, instead of being a two-dimensional grid, it's a three-dimensional grid, where we're actually modeling the terrain that data set described. And here we are actually committing one of the great sins of greatly overscaling the vertical aspects. But you can see that basically this data is showing mesas with rivers flowing through it. And this gives you a three-dimensional representation of it. Did I go the wrong way? Yes. Now we can use other techniques for illustrating this data. This is the use of contour lines. I think everybody here understands what contour lines are. They're showing you the line at which the terrain takes on a specific altitude. So we will be using contour lines of different kinds throughout this, this whole business. Contour lines and contour surfaces are key to our data. So let's look at visualizing weather data. This is, some of the biggest calculations that are done in America are weather simulations. And they're actually very challenging, very hard to do, because they have to be done at a high resolution, high quality, and most importantly, they have to finish before the weather actually occurs, right? So this is deadline-driven simulation. So we can clip away that data. Here we've defined 3 planes that intersect the domain of this function, and we're using color maps, just like we did in that earlier picture. We can put contour lines on those planes, or we can do contour surfaces. A contour surface is a 3-dimensional version of a contour line. Think about the surface in this room where the temperature is exactly 72 degrees. Everywhere on one side of that surface is going to be higher, and everywhere on the other side of that surface is going to be lower. And that provides a surface through space, which we call a contour surface, or more often, an isosurface. And so isosurfacing is one of the very fundamental visualization tools that we use throughout our visualization work. We also use vectors, use what we call glyphs. Supposing that we have the wind direction at every point in this space, and we want to somehow show people where the wind's blowing, right? One way you can do it is you can drop a large number. You can just basically ask, where is the wind pointing at every one of a large number of points, and put a little arrow there to show you where the wind is going at each one of those points. So this actually doesn't show up real well here. But what this actually shows up is a large number of arrow glyphs, each of which is showing the direction that the wind is going, and by its color and length, the magnitude of the wind, how hard the wind is blowing. So this gives you an ability to take a three-dimensional vector data set and produce a visual of it that conveys wind direction. Here's a better look at it. There you are. So here, the little blue arrows are showing you where wind is very calm. The larger dark red arrows are showing you where the wind is really blowing. So how is this data actually represented to the computer? Here's our elevation data again. So this is two-dimensional data to keep things simple. But now let's look real close at the bottom corner of that data. What we actually have in that data set is a set of points in space, longitude and latitude, and we have the values for every one of those points in space. That only gives you information specifically at those points in space. But what we also have is what we call a mesh. We tell it the data includes not only these points in space, but how they're connected into quadrilaterals here, right? So basically, it tells you that these 4 points here are associated in a square cell, and given that, we can tell you what the attribute value. We can approximate, I should say, what the attribute value is anywhere inside this square, by a weighted sum of the values that are happening at each vertex of the square. So that gives you the ability to actually interpolate data smoothly across the whole surface. So now instead of having that raw data only at the specific points, we put an interpolation model on it that allows us to represent the data continuously throughout the surface, right? And that is the key to scientific data representation. The systems will give us the actual values at particular points, and an interpolating function that tells how the data can be derived at any point by interpolating from that vertex data. Does that make sense to people? Interpolation, though, is a problem for us. So suppose that we have a slice through that elevation data that I was showing before. So this is think of this as a slice across in latitude. And this is a function that is showing you how high the surface is for every point in that domain. Okay, so this is a horizontal slice of that elevation data showing how high the surface is at every point along that horizontal slice. And this is what we call the ground truth. No pun intended. This is how high the honest-to-God surface is. If you were to go out to Colorado and actually measure an infinite number of points along this line, this would be the curve you'd get. But we can't do that. We can't do that because we can't measure an infinite number of points. We have to come up with a set of points that we're going to measure and interpolate in between them, right? So here are the points that we're going to evaluate this function at, that we're going to tabulate this function, which is going to give us those points in 2 dimensions, right? Where we know that for every one of these points along the line of latitude, what the elevation is. And then we're going to interpolate in between them. And here, it's not bad, right? The linear interpolation that we're doing between those points does sort of approximate the underlying curve. Great, we're happy as a clam, right? But if we undersample the data, if we don't have enough points there, a linear interpolation that's going to happen over that data range is not going to match real well to the underlying function. And so you can get artifacts, you can get things that show up in the image that are not in the data, but which might trick a scientist, a user of this data, into believing that there are facts in the data that aren't there. And so this is a very important part of the representation of data in visualization is making sure that the representation actually corresponds to what's actually going on. And here the lesson to be learned is that the sampling rate, the rate at which you're sampling this guy, is a critical factor to making sure that you are actually able to reconstruct the original function with some level of fidelity. Now, one problem we have, I don't know if it's a problem, it's a fact. Visualization inherits the grid from upstream, right? I mean, to some degree, we can reposition satellites to get to sample different points in space, or we can, well, let me not go there. There's a simulation that's running to model the atmosphere over Ohio, and that simulation is running at some resolution. And that's going to be the highest resolution that we have access to. So ultimately, we may be cursed with a underlying representation that's not adequate to convey the data. But then the argument here is, then it wasn't really, that's the simulation's problem and not ours, right? But there are various ways that simulations can take advantage of lower resolution grids. Everything we do is what we call linear interpolation. Simulations can do higher order interpolation. They can do spline fits between points and get better approximations of the curve, which we don't know about, we can't use. So there are some visualization applications that support those higher resolutions, but for the most part, we end up with taking the sampling that is given to us upstream and doing linear interpolation for visualization, and that's what we got stuck with. Now, often, the data that is upstream from us is very, very large. And in fact, it's much larger than is necessary to do pictures. I mean, ultimately, there's a finite number of pixels in this image here, right? And so this can only convey a certain amount of information. So if there's more information in the underlying data, to some degree, that information is necessarily lost. And so one thing we typically do is we take these very high resolution data sets and we downsample them so that there's a correlation between the resolution that we want to actually see them at and the data itself. And that way we don't have to deal with quite so much data. But that's itself a difficult problem, but one to keep in mind. So how do we represent these grids themselves? Well, the simplest possible way to do it, in my mind, is by essentially listing out a set of points, just X, Y, Z points. Where we break down this room into a bunch of sugar cubes, and every crossing point is an X, Y, Z point. And we just list the damn things, right? And then we say that the first 100 are going to be the row right along here on the floor. The next 100 are going to be the row one level up. And we order those implicitly to fill the room. Okay, so we've explicitly listed a set of points. We can implicitly describe how those points are being connected together. Or we could do it much simpler. I could tell you where this corner of you can't see that corner of the room is. And I could tell you that we're going to use a step size of a foot in this direction, a step size of a foot in that direction, and a step size of a foot in that direction. That there are 100 along there, 100 along there, and 12 along there. And that would describe a grid that fills the room, right? And we could do that with one origin point, where that point is, the delta steps, 1 foot each, and the number of points. So that's a very compact representation for that same information, right? And at the other end of things, where, as I said a moment ago, we can implicitly take that list of points and use it to describe the set of how those points describe how those points fill the space. We could also simply list the vertices that correspond to each one of the cubes, each one of those hexahedra. Okay, so I could tell you that there's a hex that contains point 12, 14, 22, 1054, and so forth. Those points are meant to be interpreted as a hexahedra. So in that case, we have not only an explicit set of points, which is going to be large, but also a single record for every hexahedra in that space, which is going to be even larger. So there's a wide range of ways to represent these grids that go from compact representations that are cheap, easy, and wonderful in many, many ways, to very expensive representations, which are explicit, where you've broken down the room into points, and you have listed all those points and listed all those hexahedra or tetrahedra or whatever. And they can, using that technique, you can accomplish different purposes. You can have a much closer representation to this room, where, for example, you subtract out the projector here. And so your description of the room, you can model the fact that that projector is here by excluding tetrahedron. Anyway, I'm going to too much of a level there, but the point is that there are a wide range of ways that you can represent this. Logically, it's always a set of points and a set of the way that they're connected into elements. But within that framework, there are a lot of different options that we'll be seeing along the way. And this gives you some idea of them. There are different grid types that people discuss. Cartesian grids are the simplest. Think about a chessboard. A chessboard is a two-dimensional Cartesian grid where every square is the same size. They're orthogonal to one another, and there's a specific number along each axis, and that describes the whole ball of wax, right? We could also consider those points as being irregular, that they're not evenly spaced. We could give them irregular points along space. So for example, if we think that there is more interesting stuff happening near this wall, instead of having even steps in this direction, we could have fine steps here and then get longer and longer as we go out that way. So we can have still a regularly connected, a grid that you can describe implicitly, but the points are now being given as irregular sets of points. Those are actually what we call rectilinear. They're spaced differently along each orthogonal axis. But anyway, so the point of this is that there are different ways of representing these grids. Structured is sort of the most abstract mechanism when you can still describe how they're interpolated topologically using a compact form where the points are all actually explicitly listed. And finally, you end up with essentially just soup, where you have a set of points and a set of elements, and there's no implicit structure to it at all. And here it gives you some idea of the size of these things. Your Cartesian regular and rectilinear grids are very, very small. Structured grids are larger because you can still represent the connectivity implicitly, but you have to list all the points. And unstructured are the largest, right? Where you have to explicitly list all of the hexahedra, all the cells, and all of the points. Does anybody want to interrupt me and ask me anything in all of this? I mean, my throat is going to go really fast if, pollen and all that stuff. So if anybody wants to ask questions, please speak up. So basically, these are fast and small. These are small. These are large. These are perhaps less accurate, and these are more accurate, allowing you, as it says here, to use finer sampling where you need it. And so these are the sorts of considerations that we look at when we come up with the grids that we represent this stuff with. Often this data is time variant, right? Weather data, for example. We want to look at how temperature changes over time. So basically now it's a function, instead of just latitude, longitude, and altitude, it's a function of time as well. So in fact, most of this, I shouldn't say most, a lot of this data is in fact four-dimensional. Here's an example of data varying in time. Let's see, I figured out how to move these before. There we are. So here is a very simple little data set in X, Y, and Z. Oops. I had it for a moment there. Now, shouldn't I be able? Yeah, there we are. Okay, so here we're looking at how that data is changing over time, right? But we're only looking at the outer surface of it. So this is really, it's not telling us much about what's happening inside that surface. So in order to understand that better, we look at how isosurfaces change over time. So if you think about this data here, this is really low resolution data, as being values that are high here and low there, you can imagine there being a contour line that lies in between them. And this is a three-dimensional version of the contour line. And we can see that evolving over time. Okay, so now this is a visualization of a four-dimensional data set using time as the fourth dimension. All the stuff's done with Paraview, by the way. Volume rendering is another technique for visualizing 3 dimensions of information, perhaps over time, where there are no nice, neat surfaces in space. Think cloud, okay? When you look up in the sky and you see a nice puffy cloud, what you're really seeing is the distribution of water vapor in the atmosphere. And where the water vapor is high, it becomes opaque, and you see the cloud. And where water vapor is low, it's not, it's transparent, and you see through to the blue sky, right? So volume rendering essentially models that. I also think of volume rendering sometimes as jello with fruit in it, right? You can have very transparent gelatin. You can put grapes in it, and you can sort of see embedded surfaces in gelatin and have the gelatin's transparency vary over space, and that's volume rendering. It's looking at volumetric data without actually deriving surfaces from the data. Is this an animation? It is. Okay, this is my favorite animation of all. This is that wave propagation. And so this is a volume rendering. Oh, I'm sorry, this is a stereo representation. So anybody who can do cross-eyed stereo, do it now. What you saw is the shock wave started here off the coast of Japan. You see this bowl shape here. Right here, it hits the core of the Earth, and this is the rebound of that shock wave after it's hitting, thank you very much, after it's hitting the core of the Earth and bounced back. So if we run through this again, you see the shock wave forming a bowl as it starts at the surface and going down. Then it hits the core of the Earth and it rebounds. Right about there, it hits the core of the Earth. And here comes the bounce back. And the bounce back, since it hit the surface, hit a curved surface, is spread out. And this is basically showing you that shock wave from that earthquake and how it hit the core of the, well, how their simulation models, it hitting the core of the Earth and returning to the surface. Okay, and this is a volume rendering. I have not pulled any surfaces out here. All I'm doing is looking at a scalar field, a field of numbers that fills the Earth here, and interpreting them as varying transparency, and you get a three-dimensional picture. And this really looks cool in 3 dimensions because you see that bowl and it's standing right out at you. And so if you can do the cross-eyed stereo stuff, you could do, I'll play it again for you here, or you can go down to the lab and we have a 3D display device down there that shows it off. Sorry? How did I make it? Yeah, we do, sure. Oh yeah, they show it on MAV, you know, one of those displays that's over there by the, yeah, I saw it in the background of a meeting we were at when you guys were in Saddle. So. Okay, I can go, at this point, I can branch off on special topics till the cows come home. Some of them are interesting, some of them less so. So before I do that, let me call for any questions or anything anybody wants to discuss. Shy people. Next time I do this, it's not going to be in pollen season. All right, well, let's look at just a few extra topics there. Some of the other issues that we deal with in the sci-viz world are the data can get really big. That's why there are huge computers over there, and this data can just be so big, it's sort of mind-boggling. Particularly, a lot of times, this data is more expensive to read in and read out and to read in than it is to visualize afterwards. So a big part of everything we do here to make visualization work on these large data sets is about optimizing the reading time as opposed to anything else like generating pixels or anything else. A big part of our goal is just optimizing the reading time. We do parallel processing. We'll be talking about this a lot more later, but in order to do these jobs in less than glacial time, we try to spread them out over as many machines as we can, and we'll see different reasons why we have to do that later. In situ visualization is sort of the cream of the crop, where you have data sets that are so large running inside simulations, you don't want to write them out at all. And so you can You can put visualization directly into simulations as they're running. So really big data is a big part of why we have a visualization team here at TACC. It's to figure out how you're going to do visualization of data that is just vastly larger than you could conceive of doing on a normal machine. We also do a lot of work with large format displays. How many people here have ever been to the Viz Lab on campus? Has anybody here ever been to the Viz Lab? A couple people have. We have a lab on campus where we have this device here. This is called Stallion. It's, I don't know if that number is correct. It's one of the world's largest displays. It's, you know, I'd say it's roughly the size of this wall here. It's 328 megapel. The device you're looking at here might be a megapel and a half or so. So there is a vast number of pixels. You can show pixels, you can show images on this thing that are not only large, but large in the sense of their scope here, but also very finely detailed. So you get both ends of the spectrum here. You get both the size of this image and incredible detail when you look close at it. It's you should come down to the lab sometime and see this stuff. Virtual reality is a really interesting subject that I think is getting to be more and more important these days. This is a sort of the standard model of visualization. Simon here is a virtual reality specialist, so he's probably going to take great umbrage at everything I'm about to say here, but that's life. This is a model of really what we do with visualization. We sort of imagine the data to be on the other side of this screen, and we project that data onto the screen, right? So in that earlier picture that showed the Earth, that showed that model of the Earth, you could imagine that as being a window, and you're looking at that data from a spacecraft, and you're looking through a window, and that window is the screen. So it's basically a projection onto a screen, right? The problem with this is that if you want to interact with what's happening over there, your devices are out here in the real world, right? So if you want to adjust something in what you're seeing, you're adjusting it with only a sort of a secondary connection between what's happening here and what's happening there. You have to have some understanding in your mind about what the effect of moving your mouse is going to be when it comes to actually dealing with the object in front of you. If you want to take that object and want to rotate it, you're going to do something with your mouse, and you have to have a notion in your head of how that mouse motion is going to be connected to that thing moving on the screen. Now, virtual reality, do I have a slide on that? Yeah, virtual reality puts you in the data space itself. So instead of looking at it through a window, you're actually there in the data space itself. And there are tricks that are being used to do this. VR glasses, I'm sure everybody knows about Oculus Rift now, things like that. They actually essentially put you in the same space as the data itself. So you can interact with it directly, right? So using handheld gadgets, instead of knowing that if I spin this that way, the object's going to rotate that way, I can grab the object and I can move it, right? It's a much more visceral, much more direct way of understanding the data because you are in the space with the data instead of looking at it through a window. And this, as far as I'm concerned, is the hot topic of visualization nowadays, is figuring out ways to do interactive, immersive visualization. This actually is a device called a cave. We don't have a cave here. Simon is an expert at caves. What essentially we're doing is we're tracking this guy's head and watching what direction he's looking and allowing him to move around and look in different directions and then painting on the surface of this box that he's standing on what he would see given that he is standing where he is, looking the direction that he is. And so it looks weird from this standpoint. You know, you really see that this is a box. But if you were seeing what this guy saw standing there, it is incredibly convincing. You will really feel like you are in that environment. It's very difficult to really understand without doing it. But the long and the short is, from his point of view, he's seeing what he really ought to be seeing if he was where he is and looking the direction he is. So virtual reality, as far as I'm concerned, is the hot topic. Caves are one solution that are very large. Remember, beyond each one of these surfaces, there's a projector sitting over here somewhere, projecting onto that. There's a projector down here somewhere, projecting onto the ground. These things are immense. They're huge. Trust me on that. They're very expensive. They are single-user devices. These things are only showing the right picture for this guy standing where he is and looking in the direction he is. So this is an immense, expensive, single-user device. And that in a nutshell, is its Achilles heel. And that's why I'm so excited about Oculus Rift. How many people here know about Oculus Rift? Oculus Rift is a head-mounted display. It is a display that you can wear like a pair of glasses, a big pair of glasses. And it replaces what you normally see with screens. And then we can detect, again, where you're looking at it from, I'm sorry, where you are, what direction you're looking, and put into those glasses what you should see. And that gives you very much the same effect as this guy's getting. But you can do that with a $350 pair of glasses and a computer that can generate just those pixels. And you don't need all the rest of the stuff. Got some drawbacks yet. I won't go into them because Simon here will get upset at me. But this is the next generation of scientific visualization. It follows on the long-standing tradition of having scientific computing being leveraged by the gaming industry. That's why all of this works. Oh yeah, so here's some of the early head-mounted displays. This was first developed way, way, way back when at University of Utah, where this guy, the head tracking is being done by a gadget that hangs out to the ceiling that is holding onto your head, so that when you move your head, it tells it where it's looking from. Oculus Rift, though, is seriously cool, and you'll be hearing much more about this. This was a Kickstarter project that Facebook just bought for $2 billion. So it's got to be the most successful Kickstarter campaign of all. Certainly the most successful VR project. We have other in-between stuff at the lab. Please, come to the lab when you get a chance. There's always, during the business day, there's always somebody down at the lab to show this stuff off. If you have kids, bring the kids. They will love it. All right. That's all I'm going to tell you now about the sort of the large picture of scientific visualization. So at this point, I'm going to let you guys take a break, or I'm going to answer any questions first, but then let you guys take a break, and we'll be back at 10:30. Any questions? Have a nice break. Do whatever.
Okay. Yeah, stay screen sharing, so you can flip back to your slides. Okay, let's get the show back on the road here. It doesn't say so on the slide, but I am, in fact, still Greg Abram. What we're going to be talking about in this section is, I think of as sort of lip service towards the information visualization side. I am not an expert at InfoViz in any stretch of the imagination, so I just sort of want to give you sort of a little overview of the whole thing. And if anybody falls asleep, I won't wake you up. All right, we're back to the platitudes section. The general aims of InfoViz are, again, to use the human ability to look at stuff and to understand patterns and things like that in order to understand large, and in this case, really abstract data sets that don't really have the sort of grounding in three space that that scientific visualization has. It, though, shares a lot of characteristics in common with scientific visualization. What we really want to do is we want to look for structure and patterns and things like that inside this data, because that's what we as humans, as people who have evolved for 3 billion years, have really developed talent for, is to look at data and see patterns and things like that. So it's very qualitative. It's looking at ways to identify the stuff in the data that you're really interested in, to pull it out. And so, again, it's very interactive. Let's see where this is going. Wrong way. Okay. Data sources are wide, varying. Possibly the classics are comma-separated values, essentially just ASCII data sets, ASCII files that contain information. Excel spreadsheets, again, are a hugely important source of data. Databases, Ingress, Postgres, all that kind of stuff. All that is, why is he looking at me through the door? All that is the place where this data comes from. And nowadays, you know, in the big data explosion that we're seeing these days, this information's all over the place. Every time you go to buy something at your supermarket and you give them your credit card, there's a little record being added to a database somewhere that is basically saying this person bought this. Actually, it's not your credit card, it's your magic number in the supermarket. This person bought these things, and that all that data is acquired. And people want to use that data in order to better, for example, position products on shelves and stuff like that. We actually did a lot of work when I was at IBM to look at algorithms where you could decide how to distribute products on supermarket shelves and whether or not it made sense to put the beer and the diapers on the same aisle or not. There are a lot of ways to, well, okay. A big problem with all this data is it usually has a lot of noise in it, a lot of garbage, because this data is not necessarily collected it's not collected automatically. It can be collected by hand. There can be a lot of interpretation that happens in its collection. And so cleaning the data is a problem in and of itself, is figuring out what data in there is wrong, what data is misrepresented. Data cleaning is a very important part of this. Then there's data analysis, how we can look at this abstract data and apply essentially mathematical algorithms to it to pull more information out than just simple visualization by itself will happen. For example, you can have higher degree, well, we'll see more about that later. But there are a lot of techniques for doing InfoViz. We're going to see more about that as we go on. So here is a data set, Excel spreadsheet. This actually came from a different class, so this isn't you all, but it is the same sort of data.
I lost my laser. Oh well. Ann, did you take my laser? Does this have a laser? Oh well, blasting off. Essentially, like I said earlier, this database is a collection of facts. There is a guy named Jennings whose portal username is that, who comes from the University of Utah, studying communication sciences, he's faculty. It's basically a fact. This person exists and has a lot of attributes. The attributes themselves can be quantitative, how old he is, so that's not in this data set. It can be ordinal, it can be something that you can order, but it's not necessarily quantitative. It can be categorical, male and female, right? Categories. There's nothing in, boy, am I getting in trouble there. You know what I mean here. Oh boy. Okay. There's no explicit spatial information in any of this. There is implicit spatial information. The universities that they come from, right? We could actually look up on Google and we could find latitude and longitude for the University of Utah, and we could figure out a spatial aspect to this data, a latitude and longitude. But there's nothing explicit in this data set that gives you that. So standard techniques for looking at that are the things that we first learned about in second grade. They're oldies but goodies. They're used all over the place. Techniques is misspelled. Line graphs is obvious. Scatter plots, maybe a little less obvious, but you can also compute regression in that and come up with approximating lines. Bar graphs, pie charts. These are all the techniques that everybody is familiar with. And in fact, 99% of the info viz that actually happens is generated using techniques like this. And that's because they're familiar, they're provided in Excel, and that's what people have to use. So let's look at an Excel example. Here is that data set. We can map data items to visual, what we call marks. A mark may be a dot to represent a position. A line can represent a little more information, areas, volumes. These are all ways of annotating visually attributes of data sets. So for example, we can take that data set and we could create essentially a two-dimensional plot where the vertical axis is one quantitative attribute. The horizontal axis is another quantitative attribute. And the dots just represent there is a person that has, at the crossing of those two attribute values, his existence. That's all it says, is there is a person that has those two attributes. Visual mapping in these marks essentially maps, as I said, data items to marks. And you can actually use multiple attributes of the data in each mark. So for example, you can use the visual properties of the mark to represent different attributes of data. Position being the obvious one, but we could actually put in another attribute of the data. If you think about that scatter plot a moment ago, we could vary the size of those points to show a third axis of data, a third attribute. For example, one of them might be age, the other axis might be the latitude of their house, and then we could vary the point being how tall the guy is, right? So that now would be a representation that there is a person who lives at this latitude, who is that height, and whatever the other aspect I have. It's actually, we can vary the dot to represent another axis of data. We could rotate objects to provide more information. Another degree of freedom in the database might be the angle at which this thing is positioned. Color can be used, shape can be used, and I don't know how this guy did it. Oh, Don't tell me I don't get that. You can actually animate, blink, do stuff like that in order to convey other information. And each one of those attributes has a different ability to convey information, okay? Position, length, things like that are very good methods because they are things that we as humans understand sort of viscerally. But you know, if it comes down to one thing being represented as a star and another thing being represented as a square, you don't really have a lot of intuitive understanding of one being greater than the other, one being representing a larger value than the other. Color, again, Terry here can tell you that humans can only perceive a relatively small number of distinct colors, right? So whereas with position, you can represent something very smoothly over a wide range of values. You can tell that something is to the left of something else. If you look at 2 points that are very close colors, it's really difficult to tell which one's more red than the other. So let's look at an example. This is a movie database that is showing 5 degrees of freedom, the year of the movie across, the length of the movie up high, the popularity of the movie being basically the size of these glyphs. The subject is the color, which is going to be categorical, and whether or not it got award by its shape. So this tells you that, I mean, we can look at this thing and we can tell certain things, right, instantly. That the basic average length of movies has not really changed dramatically since the 30s. That there have been a lot more movies generated in the 80s than in the 20s. What else can we say? We could look at this and we could say there are a lot more action movies. There's more red over here than there is over here. So we have more action movies recently. We can understand a lot about this data by looking at this. I think I decided that Gone with the Wind is behind the legend up here because it was really long and it was 1939. It was a movie, in case you young people don't know about that. But all this is pretty limited. If you look at this graph, there's a pretty large number of movies here. It's not vast, but it's pretty large. And over here, where it's starting to get dense, you really lose. You really can't really tell what's going on, right? There's too much stuff there. And so arguably, this is not a really effective means of representing that data. You can optimize a graph like that by choosing the axes that you want to represent different ways intelligently. But ultimately, you come across some fairly fundamental limitations of that kind of display. Space. These display devices are only so big, and you can only see objects, see marks in there that are a certain size, no more than a pixel, right? You can't get smaller than a pixel. So, you know, you're not going to be able to put more than 1 million marks on these things, and we have databases here that are vastly larger. So one thing you can do is you can increase the screen real estate, and that's why we have displays like Stallion. Here, we're looking at a genome. The sequence of nucleotides across this strand of DNA, there's a huge number of them, right? So we can actually put up that entire sequence of nucleotides because we have a huge display to put it up on. And there's a huge amount of detail in each one of those displays. So we can use big displays to show InfoViz of really large data sets, no doubt. However, these displays are few and far between. I would be willing to bet there's one down at UT San Antonio, but there are none in between. And it's 328 million pixels. We have some smaller displays that are 9 million and 12 million. But again, this is sort of an impractical solution, right? Because not everybody's going to have one of these devices in his office. So what we do is we look for other ways to represent this information graphically that doesn't amount to putting up a dot for each point. And we do this for a lot of different reasons. For one thing, a lot of this data is multidimensional, right? So supposing what we showed you earlier was we could show 2 or 3 or 4 different dimensions of data by using marks of different kinds, different colors, different shapes, different sizes. We can show more than 2 dimensions of information on your 2-dimensional screen, but as I said, it becomes busy. So there are various techniques we can use. We use parallel coordinates, which I think we'll see in a few moments, and we can use multiple views with brushing. So this is parallel coordinates. This, I think, is one of the really cool things of information viz that doesn't get used as much as it should. But this is a way to put up high-dimensional information on low-dimensional displays. So if you think about a coordinate system, XYZ coordinate system, you can represent a point in that XYZ space by a position in a 3-dimensional coordinate system, right? It's the most obvious thing in the world. But instead of doing it that way, you can actually rotate those coordinates, those axes, so that they're parallel to one another. And I can represent a point in 3-dimensional space by a line that contains its X coordinate, its Y coordinate, its Z coordinate, and however other many coordinates as this tuple has, by a line that connects those points in the space. So what you're actually seeing there is that line represents a point in XYZW space. People see that? This was developed at IBM back in the probably the 60s. And it's used more and more in business viz, but it is an interesting thing. So here's an example of parallel coordinates being used to represent this data set. So here we have a data set that is 1, 2, 3, 4, 5, 6, 7, 8 variables, some of which are categorical here, some of which are quantitative, miles per gallon. And here it is tabulated. And here it is using a parallel coordinates display. So now the parallel coordinates are miles per gallon here, weight here, drive ratio, whatever the heck that means here, horsepower, and so forth. And each one of those lines here represents a single element of this table. People buy that? And what you can see here is you can see some fairly obvious stuff, right? Like high mileage cars tend to be light, right? That's why you see this big chunk of lines coming from high values there to low values here. Low mileage cars tend to be heavy. There's your Escalade. You can actually see information like that by looking at these lines. Now, of course, this has, well, anyway, this has lots of problems. It's not a panacea for everything. There's actually, whereas each one of these is, you could think of as a point in 8-dimensional space, here it's a line, right? And that line's taking up a lot of screen real estate. You can only have so many axes here. And you can only have so many lines before it becomes essentially mush, right? So you can do all sorts of things like swap these columns, these axes around, reverse them. You can do various techniques to simplify. For example, if I reverse these, if I reverse the sense of one of these, instead of having these huge diagonal lines, I just have very short straight lines that are showing you a little quicker that those guys are correlated. So you can do techniques like that. There are ways of doing these things using partially transparent lines and adding them together, and people have done some really great stuff with this. But I just wanted to put it up here as a means of showing higher dimensional information on a 2-dimensional screen. Multiple projections. Here's that same data set. But now instead of trying to show all of it in one plot, we're going to do scatter plots of each variable against each other variable. Okay? So what this is now telling you is, God, I wish I had that laser. Where the hell did my laser go? But if you look at miles per gallon in the upper left against weight, that's going to be in the second one across from the left on the top. Or, of course, the second one down from the top on the left. You see that correlation between miles per gallon and weight. right? Because those guys clearly have a negative correlation. And so by looking at these guys pairwise, you can see the overall, you can get an idea of the overall structure of the data. But what you lose is, first of all, again, you are using a lot of screen real estate to do it. You're getting a lot of dots there. And you really don't have a correlation between what's happening in this guy and what's happening in that guy. You might like to know what these guys, how these guys down here appear in this guy. Whether these guys that are high in displacement and low in drive ratio, how they map in here to weight. And to do that, we use an interactive technique called brushing, where we can do selections and show color. And these techniques are used widely in the biz-viz world, business visualization world, to show this high-dimensional information and allow people to correlate it and match it up and understand this data so that they can make their business decisions. So those are giving means by which we can take unstructured data, data that really doesn't have any spatial aspects at all, any necessary connections between these facts at all, and show them. But a lot of data has structure to it. Some obvious ones are phylogenetic trees and presidential voting. Phylogenetic trees, people know what phylogenetic trees are. The tree of life. Here is a representation of a phylogenetic tree. At some point in the distant past, many billions of years or 6,000 years ago, depending on your personal opinions, there was essentially the birth of life. And from that original birth, things branched out, right? And so this gives you the notion that there's a relationship between these classes. I don't know, anybody a biologist here? Anyway, this shows you how a structure between them. That can get busy. Here we have a few tens of somethings. Here we have maybe a lot more. And the numbers I've heard for this is there are as many as 500 million, maybe I'm pulling that out of my rear end, but there's a very large number of species out there. And if you try to put up a phylogenetic tree that includes all the species, you know, it's not going to work very well. Here's another kind of structured data. Suppose that we had a data set that showed the breakdown of votes for each precinct in the country. We could break that down hierarchically, where those precincts are broken apart first by the county in which the precincts are, then the counties can be organized by the state in which the counties lie, that all lie in the country, right? So looking at this, we can see that the United States, the voting in Delaware is split among the 3 counties of Delaware, and the voting in Kent County is broken down into that number of people in each precinct. So this is a structured method of showing that information. This can be sort of carried to an extreme with tree maps. This is another representation for that same data. I hate to say it, this was also developed at IBM, I think, where we've now taken that same data set and we've broken it down by states, within each state, county, and within each county, if you were to click on this, you could see that county broken down into the precincts that contain it. So this gives you an ability, essentially, to browse that data using its structure to help you understand the makeup of the data. There's generalized relation data. This is data that comes along the categories of Bob knows Bill, Bill knows Ted, Ted knows Ann, and so forth. We can basically position those guys up there in space and represent their relationships by edges that connect the different points, right? This, of course, also can get busy this is actually a small part of a data set, if memory serves me correctly, which it probably doesn't. It has to do with paper publishing in visualization. And what you're seeing here are categories, I think, and how they are represented together in papers. You can't tell anything from this, right? Another classic example of something like this is people exchanging information via Twitter. Twitter is a source of huge amounts of data like this, and you can just create mush. So it becomes very difficult to represent any of these large, very large data sets in their raw form on any kind of visualization. We can use heat maps to represent essentially the same kind of data with weights. So now we can somehow show that Bill here, Bob here, likes Bill because it's green, but he really doesn't like Ken, right? And so using a heat map, you can show the same. What I'm trying to tell you here is, in the InfoVis world, there's an infinite number of ways to represent data, and it is your job to choose among those ways the way that conveys the kind of data that you want, the information that you need most effectively. And what I'm trying to do here is show you some of those ways. Now we can take those graphs that I showed earlier and use a force-directed layout. This is kind of cool, so I thought I'd go ahead and show this. Sorry. There we are. So here we have a data set that is representing, again, it's representing the relationships between things. But whereas we could on one hand, we could position those guys arbitrarily in the two-dimensional plane and connect them. This is what we call a force-directed layout. So I can tell by looking at these, the things that are close together here are most closely connected, if you like. That this guy likes that person because he's nearby, whereas he really doesn't like this person because he's far, far away. So this is a force-directed graph where the positions of these guys is being determined by a weight. And it's kind of cool here because I can do this in real time. This is all in a web browser. It's all kind of cool stuff. I like it. Anyway, enough of play. Oops, yes, right place. So far what we've been looking at is the raw data, is ways of taking this raw data and put it up on screens. And it is very crude, and it is not able to handle a lot of data, it's problematic. Why am I showing this? I haven't the slightest idea. Ah, right, maybe. No, I have no idea why I'm showing this. Ah, there's a place where it's erroneous. Here's a place that's telling us that there is one person in this data set from Hockessin, Delaware. Here we see that Blacksburg, Virginia, this is a case of bad data. This guy is in there, he's really from Blacksburg, but you mistyped something, and so this is the requirement for data cleansing. But it's basically going to end up with, unless you do data cleansing, there's going to be a separate little pie slice for Blacksburg and Blacksburg. Champaign and Urbana are really kind of the same place. Anyway, the point is you need to clean that stuff up in order to make it make sense. But there are other ways to analyze this data as well. And there is a lot of research that's being done in this, that has been done in this forever, but it's being done more today than before, been done before because of the large amount of data that's out there. There's ways to analytically look at this data and aggregate it and distill it and come up with representations that are more easily represented than the raw data itself. The one that you're probably most familiar with is regression analysis. We saw some of this in the earlier talk, where we just have a bunch of scatter plots, a whole bunch of points in space that we think are correlated, and we could come up with a line that statistically represents their correlation. Principal component analysis is another way of figuring out how to reduce high dimensions of data. Look what I just found. High dimensions of data, and find the important dimensions that are really carrying the discriminating values in a data set. So if you might have a data set that consists of 100 variables, it might be that that there's a great deal of correlation between most of them, and only a couple of them actually discriminate the data, actually tell you why the values are distinct. And that allows you to represent it in lower dimensional space. So clustering is finding items that are similar in some sense. And anybody who can define the word similar in this is a better person than I. That's a big part of the trick. How do you say how similar things are? And so clustering is a means of finding out what sort of clusters of data there are out there. K-means clustering, we can basically, here we're looking at the center of the locations of people who were in that earlier data set, and we can sort of see how they're distributed over the country. Boy, I'm really bad at this talk, so if y'all just want to tune out and let me finish this without listening, feel free. Terry's probably croaking here that these colors are chosen arbitrarily. Oh well, that's life. Here's another form of hierarchical clustering where we can show how this data is broken down. Machine learning is a great technique where we can sort of let the computer decide for itself what similar means. It's broken down into two different classes, supervised and unsupervised learning. I bet there's somebody here that knows more about this than I do, but basically this is trying to automatically decide the clusters in data without a person having to sit down and figure out what axes, what variables he wants to cluster in. It's kind of computerized magic. I have never really understood it. So when it comes to the tools that you can use for doing this, the fact of the matter is, a lot of the tools for doing this are the tools that you use every day, that you're very familiar with, and that is stuff like Excel. And this is a joke. 97% of all unattributed statistics are made up on the spot, and this is an unattributed statistic. So I made this up, okay? But the long and the short is, Excel is where most visualization is done. It's just a fact. So there are a lot of tools out there. There are tools for data management applications. R is a very important tool for doing statistical analysis of large data sets, but there are also database systems. There's a lot of commercial visualization tools out there. InfoViz has become a very commercially important area because people use it in business a lot. And so a lot of the best tools for doing information visualization are proprietary and they're costly. They're expensive. So whereas a lot of the scientific visualization stuff, the best tools are open source, free for anybody to download, use, modify, and so forth. A lot of the best InfoViz tools are proprietary, and it's a sad state of affairs. There are, however, a lot of toolkits that you can use to put these things, to build these things. Most of these are going to require a certain amount of programming ability, but there are some end-user InfoViz packages out there. RStudio's got one called Shiny that lets you look at data from R. And it's becoming easier to do the more sophisticated information visualization than what there was before. But the really powerful ones are things like Tableau and Spotfire. And if anybody here is interested in GIS data, Esri, Earth Sciences Research Institute or something, just completely owns the GIS universe. So just to sort of sum up here, I hope, good visualization is useful in many ways to amplify your ability to understand your data. Everybody knows that. Information visualization can also be used to obscure information. And you can do bad InfoViz and convey all the wrong stuff. And so it's kind of like statistics, right? I mean, what's the classic answer in a statistics thesis defense? What is the question? What is the sum of 2 and 2? The statistician's correct answer is, what do you want it to be, right? So information viz can be used to misrepresent data It's just a fact. But the fact is, it can be used to enhance your understanding of data and to convey that information once you've understood it. It can be done in an exploratory sort of fashion, like scientific visualization often is done. And we're now doing it in ever larger data sets on ever larger machines, as you can see across the hall. There are a lot of fun websites. You can download these talks off the web, so you can see these. Maybe these are a little out of date now, but these are probably worth looking at if you're interested in this stuff at all. I have to say the New York Times is has done a lot of really important work in developing these things, and they've got a crew there for doing information viz that is really state of the art. If you're interested in this stuff, though, I would also point you at this guy, Tufte. His work in his books are the absolute seminal foundational work in information visualization, and I would heavily recommend them. There's a lot of software that's relevant here. Python is probably my favorite for doing any kind of this stuff. Python has a package called Matplotlib that allows you to do a lot of this visualization stuff, but again, it requires you to write, code instead of doing stuff with point and click on the display. People talk a lot about previews, but I don't really know much about it. Google Charts is used heavily inside web pages. There's a lot of packages out there. If you want to build web pages to use InfoViz techniques to show information, there's a lot of stuff now in the web world for building web pages. There's tools similar to Paraview, Titan, which is also usable for this sort of thing. Mercifully, we're at the end of that section. So if there's any questions about that or just anybody cringing. Yeah?
I just have a general question. If we have some data set we're working on and we'd like advice or resources, there's someone in the biz department that we can email?
Oh, absolutely.
Like anyone in particular, or?
For this kind of data?
Yeah, any kind of data set in the future that we might be.
Well, I mean, the proper way of doing that is to get an account on our systems, which is free to be had on the TACC webpage. And then you can put in what we call tickets. And you can put in a question as a ticket, and it will get directed to the most appropriate person for answering the question, and then that person will answer your question.
Sure.
You don't have to be, part of a project or be really using our systems or anything. You just get that account, you can write a ticket. Any other questions? Okay. Conveniently, Anne has just run out on us. So I don't, let's take a momentary break until she returns. I hate that.
Is she going to work from this machine?
No, she's going to bring her own machine. So.
Screens.
you're gonna share your screen using the green button on the left.
This guy.
Top left.
Screen share.
And you'll do your entire screen.
Share.
And then
Your screen sharing.
So go ahead and bring your presentation in front of your screen.
Bring the present. Okay, well, I'm going to be actually.
Your terminal or the Paraview application, you can bring it in front and then it'll start whatever's on that screen.
Now it's like obscured. Paraview. There we go.
Downloads.
So I'll start with the slides, I guess, here, so they'll stay in sync, and then I'll just announce that I'll be doing a demo when I do it.
Yeah. I just downloaded this. Should be in.
It's called version 2, so the name is, it should be this, but underscore v2. So it's not quite the right
It
one.
didn't.
Yeah.
Now.
Yay.
Okay, so you can go ahead and, if you want to look at it like this, you have an option as far as.
Okay, I'll go ahead. I'll do it manually until I get to the, yeah, that's fine. I'll just keep them in sync.
So we have. Okay, so when you're ready to switch, just let me know. Right now it's just displaying.
No, I think it's because I have the same thing on both of them. So like if we, here, let me, so we don't get confused. So it will be, peer review will be on this one. Yeah, that's correct.
Okay, and you can hide that little window, like hit the hide thing. There you go. Now you can see your doc.
Okay. Yeah, that's better. All right.
And then when you want to go, whatever you
Okay, is it working now on the Google Hangout? Like it's ready to start?
Yeah.
They can hear me, I guess?
I see. There, yes.
Oh, perfect, okay. So just an announcement for the people that are listening remotely. At some point, I'm going to stop doing the slides and do a demo, so I would recommend that you download the slides or just pay attention to the demo. It might be confusing when you will only be able to see what's on my screen, but people here will be able to see the demo and the slides. So, but I'll let you know when I get to that point. So today I'm going to be covering Paraview, and we're going to go over the basics of how to use the GUI and then also the Python scripting interface. You don't really need to know Python to use the Python scripting interface because it's very easy to use. Paraview has trace functions which spit out all the Python that it uses, and it's very useful to use Python if you want to, say, make a movie, submit batch jobs, or just make your workflow process a little easier. Sometimes it's a little clunky to use the GUI, but it's nice to be able to get things like camera positions and set up a nice looking view, but after you've done that, you might not want to use the GUI at all. So it's nice that you have the option. Let me see if I can try to keep this in sync. Okay, so before we begin, make sure that you have Paraview installed. Does anybody did anybody do it in advance, or maybe let's just take a moment. One thing, I was going through the slides and the exercises yesterday with 4.3, and I was encountering some problems with the GUI. So I don't know, it might have just been my computer was having a bad day, but I went through everything and confirmed that it worked with 4.2, not 4.3, after having some problems. But I'm not sure, it could have just been me, and I hadn't used 4.3 before. But if you're downloading it now, I recommend using 4.2. If you already have 4.3, we'll see how it goes. Maybe it'll work. All right, I'm going to go ahead and continue. People can download Paraview. So one thing, the reason that we're teaching you Paraview, the nice feature is that the GUI is the same on your desktop if you're running it locally as when you're running it on one of our machines. So you don't have to relearn anything. There's a couple simple commands that Greg's going to teach you about later to launch it in parallel, and you click a button that says connect to server, and that's all you have to worry about. So you can become familiar with Paraview using smaller data sets or using just your desktop, and then you can use the same interface for running on Stampede or Maverick. It's built on top of the VTK library. I don't know if anybody's familiar with the VTK, but when you look at a lot of the visualization operations and commands, they might look familiar if you have used the VTK library before. It supports a wide variety of data types. Greg already went through all these before, but structured grid, so uniform rectilinear, which is just a regular grid. So in 2D, that would just be an image, right? You could import a bunch of 2D slices and make them into a 3D volume. Rectilinear grid, curvilinear, unstructured grids, point data, and polygonal data. If you wanted to just import geometry of some kind, you could do that. And time series support. One nice thing about Paraview, if you have a time series of data, Paraview, because it's designed to work with large data, isn't going to load the entire time series. It'll load the first step, and you can apply your visualization operations, and then you could hit play, and it'll step through the visualization that you set up. And how seamless or fast that will be will depend on how large your data is, of course. But if you have like the example that we're going to show you today, it's just it's in real time. It's able to play through the time series of data. Paraview supports a wide variety of data formats. Once we get to the application, if you just go to File, Open, you can see the long list. There used to be a website that had all of them on there too, but I think it's not up right now, so I changed that. That's a good way to see what the current types of files are supported. And you can also write data readers to extend support to other formats, or you can convert to a format that's already supported. The VTK format is kind of the standard. There's a wide variety of visualization algorithms, ISO services, cutting planes. Greg talked about all these earlier, and we'll see them in a second, so I don't want to spend much time talking about them since we're going to use them. And then you can also have derived variables. So let's say if you, in your data file, you have scalars representing the vector, X, Y, and Z component, but you don't have them as a vector in your data set. You can formulate the vector in Paraview. Say if you want to do a vector field visualization, something like that. It's scriptable via Python, and you can save out animations and run it in parallel distributed mode. I think I'm just going to keep going because this is kind of more how to use what Paraview does, and it makes more sense just to do it since this is a hands-on portion of the class. So the interface, the top toolbar, there's a couple different toolbars, as is the case in most applications that have redundant operations to what you can find in the file tools at the very top of the Paraview application. The pipeline browser shows where you're setting up your visualization and operations that you're selecting there. The object inspector works, whatever you have currently selected in your pipeline browser, Paraview will display information about that. So very similar to, I don't know, Photoshop or any other modern application. Whatever you have selected, Paraview displays that information in there. So it's context sensitive. And then the large window is your 3D view. And as far as the toolbar goes, they have tooltips. So if you're curious what something does, you can mouse over it. Oftentimes, when I'm first using an application, I just skip the toolbars and just go to the menu because everything is also in the menu. Oh, wait, I think, let's see. Just some things that might be useful, undo, redo in the toolbar, the camera controls. If you get lost in some way and you want to get reoriented, you can use the camera controls to align things looking down the x-axis, y, z, or reset your camera. The VCR controls if you have a animation or time series data. And then these right here are the common filters, so calculator, contour, slice, clip. All these are also available on the regular menu. And the active variable controls, that lets you select the representation and then also what you're coloring by. So solid color if you want to color by a variable. So first off, I want to do a quick demo. So the format for the rest of the class, I'm going to do this quick demo to kind of talk about everything I just mention really quickly and show you the interface. And then we're going to do a step-by-step demo where we're all presumably going to work together. But you don't have to if you want to jump ahead. I try to stay pretty close to the slides. So if you're doing this remotely, you can do just listen or follow along with the slides, and we'll try to stay in sync. And feel free to stop, and we can walk around and help you if there's something you don't understand. We kind of have plenty of time. We don't have plenty of time right now because I'm going to let you go for lunch, but we have this workshop period at the end of the day. So whatever I don't finish by 12:15, I guess I can just finish maybe after lunch. Would that work for you, Simon?
Yeah.
Yeah, and then we'll just cut visit short if necessary. If we have to, only if we have to. Yeah, they're very similar. I think it's a matter of, most of the differences are in the GUI, and for beginners, I feel like Paraview is easier for most people because it looks like a modern GUI. It behaves like you would expect. The toolbars look like they should. Visit looks like it was written a while ago, I guess, just the way, and it's a little more confusing, but it does the same thing in the end. Okay, so now I'm going to go to the demo. So that's the end result of what we're going to be doing in the quick demo. And we're going to look at some weather climate data and look at the clouds, wind, temperature, things like that. All right, well, let me try and not get confused. So people that are listening remotely, I'm going to be referencing the slides on a screen you can't see and just doing the demo from this point on this computer. So let me catch this one up. And hopefully I don't get confused. Okay. Okay, and the test drive is next. Okay, so first, here's the Paraview interface. There's toolbars I mentioned, the pipeline browser, the properties and information panels. One thing, almost everything that you will want to interact with is in this tiny panel. Often, if I'm working at my desktop, I like to just undock it and put it somewhere else because then you can see everything. But since I have a laptop and for the purposes of this tutorial, I'm going to keep everything in one place. But properties, display, and view, those are the three sections of the properties panel. Has anyone used Paraview before at all? You have. Okay, so it used to be that the display, if you're wondering why things look a little different, they kind of moved things around a bit. The display panel used to be a separate tab in the properties, and then the view option wasn't really there. They had those things somewhere else in the GUI. So that's the main difference. I think it was like Paraview 4 or something where they changed that. But the functionality is the same. It's just a little different. And there's this collapsible plus minus. I try to keep everything hidden except for what I'm using because it gets a little clunky to use because there's so much information there. So I'm going to open these files in a moment. I'm going to show you the URL where we'll get the files we're going to use for the tutorial today, and you can also access this data set if you want to look at it yourself later. So it's on, I should have put that slide first. It's on viz.tac /training. I'll put up the URL in a moment. File open. Sorry, I just realized I should. So navigate to where your file is. This is time series data, but you notice that Paraview has nested them. It understands that it has a sequence of data here because of the numbering. And hit OK, and then hit apply, and you'll notice that Paraview has given you the extents of the data. And also all of the variables that it has found. So one important thing to remember with Paraview, whatever you have selected is what we want to apply a contour filter next to show where the clouds are. So we want to have the main data set selected, and then filters, common, contour, and then notice in the, let me make this a little bit bigger. Well, It's also not ideal. Hold on. Okay, that's not really working so well. All right, well, I've docked my panel. It's funny, I'm just going to continue and deal with it a little bit later. So I want to contour by the variable QCloud. So I'm going to select QCloud. You'll notice that in value range, it has a guess. It has guessed negative 498. We want to use a value 0.001. We've worked with this data before, so we know what a good value is. It also has the option if you want to automatically use you know, like equally spaced values or 50%, things like this. You can hit the plus and add other ranges from steps, or you know, select a range that you want. Okay, and we hit apply. So right now it's colored by the land variable, but you can select hold on, display coloring. I want to just have it be a solid color. They're clouds. We'll just make them white. All right, and now I'm going to add a slice to represent where the land is. So filters, common, slice. And then notice that it has put a slice in. Let me get my pipeline browser back here. So one thing to notice, oops, I did that wrong. If I have the main data set selected and I select slice, the slice is going to be through the original data set. What I've done here is I had contour selected because I couldn't see my pipeline browser, and so now it's going to be a slice through the contour, which in this case is not what we want. It might be. Sometimes you might want to slice through a contour and get ISO lines or something like that, but in this case we want a slice up from the original data, so I'm going to delete that. Show it, well, now I've already deleted it. We'll go through more in the next example. There's more time. This is supposed to be like the quick example to wow everyone with Paraview. So filters, common, slice. So now you notice how it looks different. How you can see how it's connected, kind of like this rather than a line. So Paraview tries to give you a notion of what operation is happening in the pipeline browser. And really, like once you don't mess this up, there's really not much that can go wrong with Paraview if you just pay attention to that. Most of the time people are seeing something that they're not expecting. Like when we get to the step-by-step demo, it's probably because you inadvertently put an operation not where you intended it to be, and so things look different. So always just look and ask yourself if the thing that you're doing next, if the operation is on the subset of data or on the original data. Because right now, this is also a good time, like let's say if we look at CV's split horizontal, split vertical, if you want to look at a different view, so I split the view, a nice debugging tool, let's say if you're just using Paraview for data exploration, you can look at the spreadsheet view and actually see, you know, so this tab right here, it says showing contour 1 or slice, and you can look at what data you have here. So it's nice, and you can actually select, you know, you can select points, and you can see how they're pink. So it's a really nice tool for debugging your data visually, even if your goal isn't to make a nice looking visualization. If you want to see what is wrong with your data, you can use a combination of the spreadsheet view and a contour or slice through your data just to get an idea of what the values are, if they are what they expect, if they are what you expect them to be, and things like that. I'm just going to close that now. So now we have a slice. Go back to properties. Sorry about so everyone else, the properties panel is below the pipeline browser, but I docked them funny and I don't feel like dragging it around to fix it. But the properties panel is here and the pipeline browser is just next to it. I'll reset it again after we start the next exercise. So I want to look at where the land is, so we want it to be in the Z direction. And then you can slide this by hand, or you can enter in a value. So I want 1.001 plane, and for my display, I'll hit apply first. So it's being colored by xland now, but you can color, see, let's color it by temperature. Okay, and we also, there's a variable in here showing the height of the mountains, so we want to see that. And a good way to do that is to just warp. Let's say we still want to look at the temperature values, but we want to see how they relate to the mountains. We can select, so in this case, I want to select the slice, right? Because I want to extrude the slice surface by some amount in the height given by the height variable. So I don't want to select the original data, I just want to select the slice data, and then filters. If you're looking for something and you don't know which category it is in, Paraview has tried to group things for you, but often it's easiest just to go alphabetical and then search for it. Or there's also, I think it's alt space, where you can start typing it in. Oops, alt space, and extrude, I forget what it's called actually, warp by scalar. So you select that and then it automatically will insert itself in your pipeline. Back to properties. So properties, warp by scalar, I'm going to select the variable height. Okay, scale factor 1, let's see how that looks. A little too big. So we can update it. 0. I think maybe 0.001 should look pretty good. Maybe a little more dramatic. Something like that. Okay, that looks pretty reasonable. Okay, and then we'll color by, we'll use the temperature. So far you can kind of see how it works, right? You add something to the pipeline, then the interface properties are all in the properties panel, and things related to color and this and that are in the display. Render view is, we'll get to that later, but that's mainly just like the background color and things like that. I usually don't use that until the end if I'm outputting, I want the background to be black or something like that. Okay, so this is starting to look pretty good. There's also a vector, there are the components to the vector in this data file, but we want to make them into a vector so that we can visualize a nice vector field, right? So in this case, we want to select the data, the data file itself, not any of the filtered data. And we need to formulate the vector, so we're going to use the calculator. Oops, that spotlight. Calculator. Okay, and also notice how the pipeline looks. Everything, this is acting on the main master data set, not one of the filtered data. So we have the calculator and hit apply. Wait a second. Properties. Okay, there we go. So the calculator, there's a place for you to put your variable name, and then this interface right here is made to operate just like a regular calculator. So we're going to call it wind vector. And one thing to notice, oops. One thing to notice is that Paraview has a list of the scalars that it has found and also the vector data. In this case, we don't have any, along with some useful, in addition to useful functions like a sine, cosine, magnitude, norm. It also has a concept of unit vector. It's pretty common to want to form a vector field from scalar data. So it makes it nice for you don't have to write anything in Python. You can just use the calculator. So we want to use the components of the wind vectors are u, v, and w. So we just want to make our unit vector u times I hat plus v times j hat plus w times k hat, j hat, k hat. Okay, that looks good. Hit apply. Okay, so you don't see anything. That's just now the output of that calculator will be now we have that wind vector. So we want to visualize that. So if we looked at all of the wind vectors, it would look pretty messy. We would just see this whole thing would be full of vectors. We want to look at just a slice of the wind vector. So we want to take the calculator output and add a slice. So do filters common slice. Okay, go back to properties and in the Z, and then let's see, where's a good place to put a slice? How about there? That looks good, maybe a little lower. Okay, so in this case, we're just using the slice. I mean, it doesn't matter what we color it by. We're just going to use that as a filter to extract a slice of the data. So I'm actually going to turn it off in the pipeline browser so we can see what we're doing. But we're going to use that. That's a kind of an example of how Paraview is operating. Now that this, whatever we attach to this, will just apply to that slice of the data. All right, that makes sense, right? So we want to add vector glyphs now just to that slice. So we'll go to filters, common glyph. Okay, and go to properties. So often, if you just hit apply, Paraview tries to do a pretty good guess at like what you might want. So if you're unsure of what a particular filter will do, you can just hit apply and see. So in this case, okay, that's good. I see arrows, but way too many of them, and they look like they're a little too big. So let's change the properties. Look in the properties panel. Glyph type, notice there's a bunch of different ones you could select from. Arrow is fine. The vectors, we have the wind vector. Let's scale it a bit. Maybe we'll try that and make less sample points so we can kind of see the vectors a little better. Okay, that's scaled it a little too much. Let's see. Why? There, that looks very nice. Okay, and then let's color them by, let me go back to display here. Minimize properties. Color, let's color them by, if you select the glyph vector, it'll color by the magnitude. So let's do that. Okay, this is looking pretty good. One quick thing if you want to, so we kind of have, it's confusing since we have two different color maps here if you want to edit that. In every case, you just select whatever component you want to edit, and then in the properties panel under coloring, this show and edit affects the color map. So it makes it pretty easy. If you want to change the color map for the glyphs, then you just select the glyphs and then click its edit panel, and then this color bar panel will come up. And if you want to select from the presets, you can, this folder with a heart on it gives you some of the preset ones, or you can make your own and save them. So we're going to just select something else randomly and then close, and you can see it updated automatically. So we know this is time step data, and you can see at the top here we have time 0 of 60. So we can just step through the data and it looks like weather data. Clouds, vector glyphs. Oops. Okay, so that was that. So now we're going to start over and work with the, I'll put up the URL for the data file that we'll be working with. Need to reset everything, and I hope this resets my GUI too. Otherwise, I might just restart it. Okay. Paraview. Okay. Put up the slides really quick to get to the training. Oops. Okay. Now we're going to start with the Paraview test drive, where you all get to use Paraview. Play from current slide. So I'll just put this up briefly so everybody can download this. And then I'll go back to me just using Paraview and then the slides for people that are remote. So disk out ref.ex2 is the one that we want. It's transfer through a cylinder, I believe, something like that. And then, as you can see on that page, there's also the WRF data if you want to play with that. There's the single time step and also the entire series. Does everybody have that URL so I can?
No, it's telling you
It
it doesn't exist.
doesn't exist. Did I get it wrong?
No, it's probably me.
Okay, it's you.
It's what?
It's you. I just clicked on it.
There we go. See?
Okay. All right. Can we go back and open Paraview? Minimize that. Oh, great. I guess it remembered how I had it last time, so I'm going to actually have to try to fix it. Okay, doc. There we go. All right. Okay, so now we have, I have the same view you guys have, the pipeline browser on the top and the properties panel on the bottom. Let me close this window. So I'm going to try to maximize the properties panel so everybody can see what I'm doing. So we're going to go ahead and open the file you just downloaded. So navigate to wherever you put it, disk out. And one thing, if Paraview recognizes the kind of file format you have, it will automatically open the right reader. Sometimes that doesn't work. For example, if you've named your file something, the different extension, you might have to specify to Paraview what kind of file you have. Okay, so now, I don't remember if I mentioned this explicitly, but another important thing about Paraview is you always have to hit apply. It's designed to work with big data. So think about, if you had a really large data set and you set up some visualization that could potentially like lock up your machine, you might want to think about it a moment before you hit apply. So if you forget, sometimes it's annoying if you're not used to that because you basically have to hit apply constantly. So we hit apply and we can see the outline of our data. Okay, let me try to stay in sync now. So today, we're going to use this data set to create an isosurface for a scalar variable, clip and slice the surfaces, use glyphs to display a vector field, streamlines to show flow through the vector field, slices, and then volume rendering. And then the most important part is actually the last part, which is the Python scripting. So I'm going to try to go through this stuff pretty quickly because it is pretty intuitive. That's a nice thing about Paraview. I think it's already, from the demo that I've shown you before, pretty easy to use. You just select as long as you have your idea of what's happening in the pipeline, edit the properties, pretty easy to do. The real power comes, I think, is when you can combine that with Python to do more things. All right. So everyone's opened their file. Make sure that all your variables are selected. You'll notice that not all of them are selected here. So what's going to happen if I put a filter after this step and I haven't selected the variables, it's like they're not there, they're not loaded. So I'm going to go ahead and load all of them. We're only going to be using some of them, but just go ahead and load them all. Okay, and then hit apply. Okay, and you'll see the cylinder. Now, the active variable controls here, you can change what it is colored by. So if we want to use pressure, we can see, I don't remember, oh, I selected the wrong one, global element ID. I was about to say, I don't remember pressure looking that way. That's better, that's what the pressure looks like. All right. And then you can also change the representation from wireframe, volume, surface with edges, so you can see what the grid looks like, rectilinear grid, surface, points, etc. So we'll just stick with surface with edges now so we can see what the grid looks like. All right, and then click on the display panel. Let me minimize this. Okay, and then notice that whatever you do up here, the active controls at the top is reflected in the properties panel too. So you can see we changed the pressure and the surface with edges. You can also do the same thing from the display panel. And then the color legend, you can show or hide it using the show icon. And then if you want to change your view around, the cylinder, so those don't really do anything. But if you want to, it's especially useful if you get lost. Sometimes if you're doing something with your data set, you get oriented in a strange way. So we're just going to click the +Z. Okay, now we're going to add a filter. So go to Filters, Common, Contour. Okay, so you should see that. This is just a reminder in the notes that shortcut Alt space is really nice for finding things. If you don't know what category it's in, either go to filters alphabetical or do the Alt space and just type it in. Makes it a lot easier than going through the menu. And then escape if you want to get rid of it. Okay, so now we're going to contour by temperature. Go ahead and hit apply. So Paraview, this is Paraview defaults right here, and we're going to select temperature. So we want to look at where the temperature is 400. Oops, sorry. One. Temperature 400. Let me try to keep this. So contour by temperature, enter 500 or 400, click apply. Okay, so now you can see. So if you want to see the, you can hide and show. So the representation we have with the surface with edges is here. Color by pressure, we can hide that and we'll see our temperature surface. Okay. So I'm going to go ahead and make the main surface just wireframe. I want to look at that as a reference, but I don't want, I want to be able to see the contour in the context of the entire object. Okay, so everyone should see. If your desire is to follow along, you should see something that looks like this. But also, if you feel comfortable with Paraview, feel free to explore whatever you would like, and then we can help you individually when we have more time and over lunch. So now I'm going to use the extract surface filter to kind of get the extract surface filter basically just gets the outer surface of your object. So we just want a representation of the shell. So I'm going to select the disk itself and then extract surface. So the reason we're doing this, oops, that's not Alt, is we want to clip through it. Yeah.
The work data you had before, was the original data for that a .nc file?
I don't know. I think it's Carla. It was the one Carla used to always use as a demo before. I'm not aware of its origins. Why?
Because we have a question on that question.
Oh. Extract surface. Okay, there it is. Hit apply. Okay. Now we want to clip that surface.
Yes.
So we'll go to Filters, Common Clip. One thing to notice that all of the common operations contour clip are right above the pipeline browser too. I try for the demos to always kind of do everything a consistent way, but you probably won't want to always go up to the menu once you get comfortable. So clip. You open up the properties panel. Show plane is checked, so that just allows you, sometimes you might not want to see the clipping plane if you want to look at your data. But again, as was the case in the work data, you can move this around and then also change the direction of the normal. So if you want to like clip it from the inside out or vice versa, you can change that. -1. Oh, we want the Y normal, sorry. Y normal. Okay, and hit apply. So now we've clipped through the data. And then we can unselect show plane just so we can clearly see through the data rather than see the box there. Okay, now I just want to bring your attention to the pipeline browser again, and you can see how we've clipped through the surface that we extracted, right, but left the contour intact. So that's another key thing when you're building up views in Paraview. Keep that in mind. Whatever you're operating on is going to have the output of whatever you applied before in the filter. So we clipped through our extract surface and left our contour, which is what we wanted to do. Now we want to slice through the surface. So we're going to slice through the entire surface. We're going to go ahead and select the main data set filters common slice. Okay. We try to stay. Okay.
Are people following here, or do we want to slow down a little bit?
Yes.
So you want to slow down? Okay,
let's
yeah.
slow down. And
Sure.
So, let me look and see if we can bring people up to stage.
Yeah, I'm so curious.
Yeah, if anybody is wants to move ahead, like I follow exactly with the slides pretty much. But does anyone need help?
Okay. So, yeah. I know. Upload on the contour. So, I have, is this about what I expected to see?
Yeah, all right.
So then, extract surface. Where was that?
That was in filters.
And I'm doing it on the original thing. Filters, comment, or
It's just I was wondering how it's everything's there. Yeah, and then just apply. Its default behavior is already on just the outer surface.
Yeah.
And then we're going to click through that surface. So we just want to, it's selected, it already is. Select clip, filters, common clip.
okay. All right, so take it off.
Oh, thank you.
So if I go to this, okay.
Other questions?
Right now, it's because its visibility is off.
Visibility.
Yeah.
So there's the wireframe.
Yeah.
The contour.
The extract surface is just it just returns polygons on the outside of the data set. The original data.
I'm showing the
It
pressure.
should just be it depends on what you select, but by default, it would just be like the grid. Yeah, the outer surface.
Okay, so now,
That looks good.
Oh.
okay,
Oh.
so now,
So the next thing I did was to slice.
and I'm still slicing the original.
Yeah, and I actually haven't gotten that yet. Not opened that yet. Next thing I have my slice.
Alright.
So I would expect pulling up the outer surface of all the electric data. Okay, so given that, we wanted to.
It's clipped.
Yes, you just go to filters. So the ways to do it, I like to do it like this, keyboard shortcut, and then just start typing it in. So it's just alt space, extract, or everything is under alphabetical. It just kind of extract surface.
Oh.
So right now it's being colored by.
So we needed to do extract surface.
Yeah.
Because you want to clip the extract surface. So what is the extract surface? The extract surface is the outer boundary. Soft.
So we're not seeing the pressure that we didn't select in the original data set. Contour.
Okay, so now you have. So you want to do contour. So you got something.
Oh, I see, so that's right.
This is 42.
Oh, they do that.
Whatever you select, now contour by seeing where the 100. Yeah, and then extract surface. See that's the outer surface of the data. And now
run this guy because this is better.
You want to add it? Yeah, so we're going to have that one selected. And then
So, because you have to choose a variable color. So this is solid color. And the white one, what's over here?
so the Y direction, and then we want the normal that leads to the inside out option.
That I think there's a constant. So what you really want to do is choose the colors. I don't know. Yeah, that's what I have. What are you coloring the copper by?
It was, I can't remember what I did originally. Color by the side temperature.
But it's an isosurface temperature, right?
Yeah, I think I meant to do it by pressure.
Pressure.
Yeah.
So
I noticed some people didn't select all the variables in the beginning, so it's not showing up in the subsequent steps to select pressure or temperature or. And it really doesn't matter. This is just a demo, but something to remember is to always select them all in advance, otherwise you won't be able to.
pressure. Put the variables there.
Yeah.
Go back. Now you should go back to one. Now, highlight config. You might have that see discover, and now look down here, you should see all those other variables. Yeah, so now you can.
Yeah, I have to see after that. I see.
Other questions?
I'm gonna see after that.
It is awkward trying to follow along, so.
Yeah, maybe, since we only have 15 minutes, let me think, because I want to make sure we get to the Python part.
Yeah, we can go back through this later this afternoon, help people step by step.
Yeah, I really feel like, because all of these exercises are just kind of designed to get you familiar with the interface, but really, I mean, one filter is kind of the same as the other, right? Depends on what you need. So I feel like depending on your own individual data set, maybe you want a volume rendering, maybe you want a clip, maybe you want a slice. But I think, does everyone get the basic idea of how it works? So let's just move on to the scripting part so we don't miss anything. And then I can go through this more step by step later if you guys want. Does that sound good to everybody? Okay. So let me just look at my slides.
Yeah, we'd be happy to go through step by step.
Yeah, and really, like if you look at the slides, it really is like click this, then click that, then next. So you can go through it step by step at your own pace. Maybe that would be more productive. It's kind of hard to have everyone stay in sync, I think, but.
There's also a very wide range of tutorial information on Paraview that's online on YouTube and stuff like that.
Yeah.
We want to give you the feel, the salt, the feeling of it here.
Yeah, and everything, all these operations in the tutorial is, I already showed you in the quick wharf demo. It's all the same things except for volume rendering, but that's pretty simple. Okay. Okay, so now, wait, are these out of order? Oh, I think there's some things weird at the end of the slides, but it doesn't matter. Okay, so now I'm just going to quickly, we're going to start over and see how the Python interface works. So I'm just going to click this button right here that's kind of disconnect from server, but it also resets Paraview. So if you go to Tools, Start Trace, we'll go ahead and just put all properties, okay? So just right off the bat, start trace, and then I'm going to open the same file again. So I can just go to Recent Files and select that again. Select all the variables. It should be, actually, hold on. There's an option that allows you to see the trace as you're doing it, which is what I meant to select. So let me do that again. Tools, Stop Trace. So you can see how it generated, you know, everything from opening the file, selecting the variables, everything that I did. It is giving you the Python for which you can run with PV-Python independent of the Paraview GUI. But I'm just going to start it over so we can see it as we go. So tools, start trace. Oh yeah, show trace as it's being generated. A lot of the times you don't want to do that because it tries to update as you're trying to do things and it's annoying. But for me, I want you to see what's happening, so I'm going to go ahead and select that. Hit apply. I'm going to use all properties and OK. OK, so let's do this again. File, open. So we can see what Paraview is doing. It created an Exodus 2 reader. All of the stuff that it needs to do to understand the data format. And then I'm just going to do, you can do anything. We're just going to do one thing just for the purposes of demonstration. I'm going to just add a contour again. Filters common, oops. Filters common, wait a second. I didn't hit apply. Okay, sorry about that. Apply. Okay, apply, filters, common, contour. Okay, and then select temperature again. $400. Where did my wait a second. I think I got, oh, here we go. Okay, I was just way zoomed in. All right, and then color by. So this is going to be kind of not ideal because Paraview is actually capturing everything I'm doing, including the camera motions. So it's going to look a little funny since I messed up there and was way zoomed in, but it'll be okay. So we'll go to filter or tools, stop trace. So whatever you've done now, you can see that you have a record of. Oh, actually, no. It looks like it didn't get all of those camera motions, which is good. So let's say if you wanted to create a series of animations, of a series of images in Paraview, you could do something like this: file, save screenshot. Oops, wait, hold on. Start trace again. Show trace. Okay, so save screenshot. Okay. Test 2. Okay. And then let's move the camera a little bit and then say file, save screenshot. Okay. Test 3. Okay. And then let's look at the trace. So you see we have like the cameras doing stuff that we did manually. We saved a screenshot. We did something else and saved a screenshot. So you can kind of see if you wanted to do something like programmatically spin the camera around, even without knowing Python, you can kind of recognize that you need to do something with the camera object and change its position programmatically. So I kind of have an example. There's not Paraview. Hold on, let me go back. So this is what you see. You see something like this where you move the camera, you wrote out an image, you move the camera, wrote out another image. So if you want to do something to move the camera around programmatically, you could get active camera. So all of these, in addition to stop trace, looking at what you've traced, you could also look at the Paraview Python tutorial, and between the two to see like what you can do from the manual versus what you see in the trace. You can put together what you might want to do to animate programmatically. So in this example, I want to change there's the azimuth and the dolly to kind of change the angle and the pan of the camera, and just change that so it spins around and does something, right? So I'm going to replace the camera motions with, let me bring this up again. Oops. Oops. Let's see here. I want to change that. So here we have the screenshots that are saved from us moving it, and just change that to having getting the active camera, setting a number of runs, going from I0 to the number of runs, and then just incrementing the camera position in some way, and then saving out an image like that. So we can very quickly save out 100 images, correct? So then you can just run everything through PV Python. If you have it on your Mac, then you have to, it's in Applications, Paraview App, Contents Bin, PV Python. But if you're running on our machines, then if you've loaded the Paraview module, then you can just execute PV Python directly, which you guys will see later, I assume. Okay, so now I have my test script, and I'm just going to run PV Python to launch it. It's saving out a bunch of images. Now you can see them all on my desktop. We have the 2 test images that I made, and then all the camera ones. So it's just kind of rotating around. So I want to quickly make a movie using FFmpeg. So are any of you familiar with FFmpeg? Okay, it's really, really fast and easy. It's not the best thing. Sometimes if you want to have a very high quality movie, you have to be careful with the options. But I'm just going to use the low quality version just to see what frames we've generated. So FFmpeg-I. I'm indicating the entire series. I'm going to make MPEG called new cam. And it's done. So we can see what we've done with our script. Where did it go? Here we go, new cam. Okay, so it's spinning around. So there's a lot of other things that you could potentially do, and we could do that more in the workshop if you guys have specific questions about what would relate to your data. But it's really easy to look at the code for clipping or camera motion and edit them slightly or according to what you need to make the common operations in the GUI into a script. Does anybody have any questions about that? I also really quickly, I had made a note to quickly go over the animation panel itself, because you said you were interested in that, right? The Paraview animation? Okay, well I have 4 minutes, so if no one has questions. It's really easy. I don't really know how to use it very well, but I could show you the basics, and then we can go over it more later if you want. But so here we have this example. We want to make an animation. Paraview also has an animation panel for, let's say you want to do the same thing I just did, not with the script because you don't want to use Python. That's fine. There's a way to do it. Under Tools, or is it View? View, Animation View, brings up the animation panel. And so you notice you have time, start time, end time, so 0 to 1. So sequence mode means it's just going to sequence through the frames. We want real time, just so it's easier to understand what we're doing. So I want to make a 10-second long video. Notice here there's a little plus sign where you can add different components to your animation. So first let's do what we just did and add a camera. Okay, so I put camera, there's a bunch of things, follow path, follow data, or orbit. Let's just do an orbit and then add that. So it has some things. We want the center to be 0, 0, 0. We'll hit OK. Okay, and let's just see how that looks. So you go up to the VCR controls and we see it's going to orbit. But you can also do neat things from this too and add whatever things you've added to your pipeline will show up here. So if you notice the drop-down menu, there's also the contour. So let's say we want to like slice, go through a bunch of different isosurfaces, or slice through the data. You could do something like that too. The key thing is you have to set that up in your pipeline first, and then it will appear on this menu here. And right now we just have one thing, so we're gonna use that. Use the contour isosurfaces, and if you click on the timeline itself, at it, you can see options for editing it. So now there's like an interpolation, values, the start time, the end time, and what values it's going to go through. So we'll just keep it as it is, just to see, and then hit play. So you can see it's going through the isosurfaces in the range that we specified. So is there anything else anybody wants to add to C? Or I mean, I guess you could do that yourself if you have it on yours, but it's fairly easy. That's the all I know about the animation panel. But that's why I said it'd only take a couple of minutes. But according to whatever you want, it's fairly easy to set up animations that way too. And also, if you want to, all of this would also be in the start trace. So if you want to do something hybrid where you have the animation set up here, but then you want the Python script for that, you can do both. So you don't have to pick one or the other. If you want to, if it's easier to set up things with the camera, which it often is using the GUI, then you can do that and then change something else in the Python script. Or I've had some cases too where I've been working with larger data where it just won't load in the GUI, like large molecular data, but I've done what I've wanted with a smaller data set in the GUI and then made the script and just substituted a larger file in the Python script, and it worked that way. Well, it wouldn't work in the GUI. Or sometimes it's just too slow because everything lags when you're working with really large data. So sometimes you can do something like that where you set everything up using a smaller data set the way you want, and then you could substitute a larger data, set it up on your desktop using a small data set, and then launch a job on Stampede with a larger data set, and sometimes it works. It kind of depends on your data. In the molecular data case, it was perfect because everything was similar, the coordinate system was similar. I just had a larger molecule where everything else was the same. Any questions? It's lunchtime now, but like I said, we can go over more of the GUI stuff after lunch, or, yeah?
How could I make the
How can you make it?
Yeah.
You mean just like you want to convert your own data into BTK? I would use just like the Python library, probably. It's the easiest way.
That's fine.
But what's the format? Is it like points or a grid?
Yeah, I agree.
A grid?
Well, if it's just a text file and it's not alone in a format, you're going to have to write code to do it. And what I would do personally is I would run a Python to parse your file and create a BTK object and then write that BTK object. So if you'd like to talk about that at the end of the day, I think you're welcome.
Yeah, if you use the Python BTK library and you have data that resembles a grid, it's pretty easy to, if you tell it the extent of your data, it can write out a BTK file pretty painlessly if you use the BTK library.
Funny, I've never found it.
Okay, any other questions?
We do not provide lunch. We have no cafeteria. So there is a cafeteria available not far from here. I'd be happy to lead you to go over there. Or there is other stuff nearby. So,